Hello and welcome to my class. I'm Grolin Annalisi from ThinkMO Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 5834444290. Today's topic is ACL, NAT, and SDN. We talked about some basic concepts of ACL in the last class. Actually, ACL is based on the current network status. When the communication has been completed, then go to do some corresponding control in a targeted manner. Then control access between some data. So let's talk about the experimental part of ACL now. Let's practice. Look at this picture. This is the experimental environment. The requirement is simple. PC1 cannot ping PC2. But today, I'm going to teach you some configuration commands that we haven't learned before. Everyone will find there is a PC1 on the left. It is on the 10.0 network segment. There is a PC2 on the right. It is on the 20.0 network segment. In short, both of them are across network segments. There must be a gateway in between. So here the gateway is introduced. Since there are two devices in the middle, definitely the device we're going to configure accordingly. First, I need to make sure the network can reach the device on the right. That is to say, these two devices need to run the corresponding routing protocol. Then let's configure them. Today our configuration is done on the device R1. That is, I hope that when PC1 goes to ping PC2 again, traffic sent. But it can't reach PC2. This is what we call access control. So we need to be on the left interface of the R1 device. Hook up the ACL. That is, configure the corresponding ACL policy on it. Then intercept the data under the interface. When I send data through this interface, after being matched by the interface, then we intercept the message that PC1 wants to ping PC2. It will not be forwarded by the router. In this case it will not be able to ping. This is what we want to achieve. Then let's see how to achieve. Before we realize the requirements, definitely have to do some basic configuration of them. We need to configure some basic addresses for PC1 and PC2. First is PC1. We directly configure the IP address 192.168.10.1. 24-bit mask. Gateway is 192.168.10.254. This is PC1. PC2 is 192.168.20.1. 24-bit mask. Gateway is 192.168.20.254. Okay. After configuration, we are going to run the corresponding routing protocol on the router. It starts slowly. We are still running OSPF. Although you will learn EIGRP in Cisco, including you will continue to learn in the future. But to be honest, it's really not used much in the network now. There are many application scenarios of EIGRP before, but not anymore in recent years. Or equipment. So let's see. We still run OSPF. First do some basic configuration. Let's name it first. A lot of content today revolves around experiments. By the way, everyone will also review the previous experiments. This is R1. The right device is the same. This is R2. Remember how to run OSPF? Before running, we have to configure the address for it first. E01 interface. This is interconnected with PC1. Its address is 192.168.10.254. It has to be the gateway of PC1. 24-bit mask. Then we go to the E00 interface. The address is 12.1.1.1. Then go to R2. R2 is the same. 00 interface. 12.1.1.2. Then the 01 interface. 192.168.20.254. OK. After we finish the basic configuration, start configuring OSPF. First configure a process ID. Suppose the process ID is 100. Router OSPF 100. We will not enter the router ID here today. We just declared. I teach you a new way of declaring. This way of declaring that we haven't talked about it before. But you can do this as an experiment. Definitely don't use this at work. 0.0.0.0. 0.0.0.0. Area is also 0. This is how we declared before. For example, there is a 192.168.10.1 on the left. Then I declare 10.0. Then R1 and R2 are interconnected here. I declare 12 network segments. Neighbors between them. After declaring the directly connected segment, pass routing information on both sides. Then we declare that 4 zeros are the full declaration. Full declaration. Declare all the interfaces on the current device. Look. All are 0. Mask is also 0. Full declaration. Once you enter this command, both interfaces of R1 are fully integrated into OSPF. Here is a simplified command. Sometimes, you want to do some low-level configuration through OSPF. Then you can go for a full announcement. But if other experiments you do in the future will be related to the details in OSPF. For example, there are a lot of routing entries. Then you probably want OSPF to be more granular. Don't do it this way. But this can be used for your daily experiments. OK. Router OSPF 100. Then declare. Full declaration. When we declare done, we'll just wait here at R1 for a while. Let's check the routing table. It will be slightly slower. OK. It learned the route of PC2. We have to wait a while. So OSPF does have a bit of waiting time. This is learned in OSPF. The route of R1 to network segment 20 is this segment. It has learned. This is the OSPF we talked about earlier. We can then let PC1 go to ping PC2. First test their communication. Ping 192.168.20.1. It works now. PC1 is 10.1. PC2 is 20.1. OSPF is running in the middle. The two PCs are connected. Then I now hope that PC1 cannot ping PC2. Before we configure, we're going to review the ACL first. First of all, it must be configured according to actual needs. Now this is the need. Actually, we can do configuration anywhere. You can also try it after class. It is also okay to do it on the left interface of this device. But because the source IP of the layer 3 IP address will not change, including the peer service you visit will not change, you can do the same under this interface. Then we will configure it under the left interface of R1 today. I don't want it to ping right now. If I intercept this data, I mentioned ping. What can you think of? This ping we send must be a message. Then when I go to ping, I am sending an echo message. It is an ICMP message. It is divided into two. One is request. One is reply. Echo is request. Echo reply is reply. Actually, You can kill the request or you can kill the reply. But we usually kill the request. Because it's more crisp. Don't let this message pass. So we configure on R1. Now we have finished the basic configuration of R1. So now I'm going to enter the ACL on R1. We haven't talked about ACL configuration before. ACL is called access list. Let's enter a question mark to see. Here, as we said before. 1 is standard ACL. It is from 1 to 99. 1 is extended ACL. Is 100 to 199. Actually, there are relatively few scenarios where basic ACLs are used. As a basic ACL matches the source IP. For example, if you are now denying the source IP of a data. So now this source IP can't go anywhere. As long as this interface deny it. It cannot access all network segments and services in the rear. So, this is equivalent to directly limiting the overall communication capability of this address. Such lethality is too strong. So actually, we don't use a lot of basic ACLs. We actually use more advanced ACLs in our lives. For example, this is a server. I can do it. Can't ping this server. But you can remotely telnet to this server. We'll have a comprehensive exercise in a moment. I'm going to show you this part. That is, although PC1 cannot ping PC2, but it can log in remotely. So now the equivalent of just hope it doesn't ping. We call such a function ping ban. But PC1 accesses other services. Or provide it. So we cannot directly deny all traffic from PC1. Otherwise, PC1 can do nothing. We should use advanced ACL here. Its overall number is between 100 and 199. We will enter 100. Here is a deny and permit. Don't worry about the remaining two. We know these two at this stage. We must deny its traffic. Deny. Then you can see the message here. Various protocols. Then there is one of them called ICMP. We just want to deny its ICMP message. That is, deny one of its ping packets. After we enter ICMP, enter another question mark. Here is a source address. As source address, it can be a network segment. But you see there's a more precise one under it. A single source host. It's called the target host. I give a simple example. For this picture. Now PC1 is 10.1. If a switch is connected under this device now, the switch is connected to a 10.2 address here. Same network segment as PC1. If you are now on this interface of the router, deny such data from the entire network segment of 10.0. Then in the future when 10.2 goes to ping 20.1, it also can't ping. So often, our requirement is that PC1 cannot ping PC2. We will not target the entire network segment where PC1 is located. Use the entire network segment of the address. We don't do that. We often choose this host. That is, use a single exact host address. Since we want to limit PC1, just let it match the overall flow of PC1 precisely. Only affects it. In the future, if there is a device on the same network segment as PC1, they have nothing to do with ping PC2. So here we do intercept. Only for such a precise IP address. So we use host here. We need to configure the address of host A. 192.168.10.1. Then I will put a question mark. Here is a destination address. There is also a single destination host below. So we still hope that it can go to 192.168.20.1 alone. Mean the same. I just hope it can't ping PC2. In the future. If PC2 has a 20.2 on the same network segment, then PC1 is also allowed to ping through. So we minimize the range of lethality. Remember my words. When we are doing ACL in the future, what do you need? What kind of corresponding configuration do you make? Do not go beyond what is required. Okay. This is an exact address. Enter a question mark at the end. This is when we limit ICMP messages in the future. The following parameters you can configure. Let's find out which one is the parameter we want to use. It is this. Called echo. I hit enter. Then exit. We can look at the configuration of the ACL. Access list. I configured a 100 here. This is the high-level ACL of 100. It has a number of 10. Deny the echo message in the ICMP service. From host PC1 to host PC2. We specifically enter such an ACL. But you will find we seem to have not entered the previous 10. It is a serial number inside the ACL. You can also understand it as a number of ACL rules. Multiple rules can be defined in an ACL list. There is such a containment relationship between them. So what does this 10 mean? For example, I will now enter another access list 100. I add a deny ICMP to it here. This is optional. We do not currently have such an address. 192.168.10.2. Then the destination address is 192.168.20.2. Then we type an echo. I just typed 10.1 and 20.1. 10.2 and 20.2. Let's enter another one and see the phenomenon. This does not affect the configuration we will wait for. Deny ICMP host 192.168.10.3. Then enter a destination host. 192.168.20.3. After we have entered, check out the command just now. You will find. Now there are 2 more in the list. You will find that their overall order is. Starts with 10. Then 20. Then 30. This is called the step size of the entire rule. You can define your own rules. That is, you can define this serial number yourself. If we don't define this ordinal, it starts with 10 by default. And then accumulatively. 20. 30 and so on. So now you can see that there are so many matches in it. The first clause means it denies the ICMP message from 10.1 to 20.1. Its second article denied this again. The third deny this. What do you mean by this? I give an example. If we go to match. For example, there is an ICMP echo message from 10.1 to 20.1. It will be matched by the first. If there is a 10.2 going to 20.1 now, then it will compare. It will compare with the first one to see if it can match. Can't match. Because the source IP is different. Then it goes to match the second. Can't match. Because the destination IP is different. Then it goes to match the third. Can't match. Because the destination IP and source IP are different. If a data comes in Cisco, it does not match any of these 3 rules in all lists. Then we will discard this data packet. We will deny this data by default. That is to say, for Cisco, if we are doing ACL configuration, there is no corresponding matching item for some data in the ACL. Then after you call under the interface, Cisco will have a default command called deny any. That is, if for a data you did not deny or permit it, then it is deny by default. For example, now comes a 1.1 to 2.2. When you come here, you will deny by default. Because although it is not clearly stated that This is a default configuration. Sometimes, everyone go to other places to configure commands. You have to pay attention to this. That is to say, when we are configuring Cisco, there is a very critical order. You must know. What we just entered is access list 100. Then let's permit here. When I now permit, I enter a question mark to see. What I am doing now is the configuration of advanced ACL. Then inside I should go for the next parameter is IP. In the ACL, if you don't know what protocol you're matching, that is, no clear rules. Unlike the demand we are talking about today. Can't ping. Ping is an ICMP packet. You only know now. I don't want PC1 and PC2 to access. But there is no explicit access restriction. Then we use the IP. You can see that it is written after any Internet protocol. Now all these agreements you can see. In fact, they are all Internet protocols. Both belong to the protocol of the IP layer. Of course, some are higher. But I'm going to tell you. If you don't know what to type, you just enter the IP. It will match the service on all of these now. We enter the IP here. Later it writes source address. You need to let go. Or, how much traffic do you need to specify? How much to enter here? We want to allow traffic from any to any, which is equivalent to, in Cisco equipment. You finally finished configuring the ACL. To enter a command like this. Otherwise, as long as you don't make explicit data, all are deny. Then in the future, there will be a lot of internal hosts that will not be able to access the Internet. You must enter a command like this. Permit any. That is, all future traffic from anywhere to anywhere is allowed. I just deny the rules I just made in it. This last command must be remembered. It shows in the list. Is such a concept. That is to say, source is any. The purpose is also any. We allow all traffic. The whole list is now complete. I have sent ICMP request packets from PC1 to PC2. It's all denied. Now PC1 seems to be able to ping PC2. Because we are now only matching the parameters. And defines the matching action. The matching parameter is PC1 to PC2. The matching action is deny. But now there is no hooking under the interface. Then I told you. If you want the ACL to take effect in the future, you must mount it under the interface. Also called calling. Because in the end whether it is deny or permit, all need to be done through the interface. So we're going to start looking for interfaces now. 01 interface of R1. Let's take a look at the configuration. Interface E01. After entering this interface, we're going to enter a command that calls IP access group. We'll just put 100 here. After that here is a direction. There is an inbound inside. And an outbound. They are packets in the incoming direction and packets in the outgoing direction. We enter in here and it's okay. After typing, let's use PC1 to ping. Or this command. Let's go to ping 20.1 again. It doesn't work. And not only. It also shows these here. It means now it is denied through some behaviors configured by the administrator. It is an unusual communication situation. This is before being denied by the administrator. This is normal communication. Now this is a communication denied by us. So above this is what we are talking about advanced ACL. Next, let's briefly talk about the basic ACL configuration method. Let me demonstrate the configuration command. I won't give you an example for the scene. For the back. Because the number I entered is 10. Then it is a basic ACL. Everyone can see. I enter permit in the back. We can do some configuration. Then let me show you. This is the host. This is any. Let's not talk about it. Let's talk about this segment. For example, I have entered the 192.168.10.0 network segment here. I can enter a 24-bit mask here. But we can enter a question mark before entering. You will find there is a thing called wildcard bits. This is a wildcard. We mentioned wildcards when we talked about OSPF. EIGRP and OSPF use anti-masking. Subnet mask is called positive mask. But in addition to the subnet mask and the reverse mask, when we make the announcement, we also have a close one called wildcard. I enter a bar 24 here. After entering this command, show access list 10, you will find I released a 10.0 network segment here. Then it writes a wildcard 0.0.0.255. You see, although I input a bar 24 forward, but it writes 0.0.0.255. Let me give you another example to explain what this means. In fact, for the current wildcard scenarios only in the first contact in the ACL, you will have more understanding in the future. When you get in touch with each other slowly. We are just talking today. For example, I enter another command. Access list 10 permit. 192.168.1.0. 0.0.0.254. Then I enter another command. 0.0.254.0. You'll find I can still type in. Let's check. I have now entered 3. This is the basic ACL configuration mode, followed by wildcards. Let's see. The first is 0.0.0.255. The second is 0.0.0.254. The third is 0.0.254.0. This looks weird. Let's talk about this. Because we actually use less basic ACLs. So wildcards are more worth talking about. Let's talk about this. First for the mask. Mask is the 24-bit mask we say every day. A configuration where we assign addresses to interfaces. 3, 255 and 10. It is made up of consecutive 1s and 0s. And it must be 1 first. Then 0 after. Cannot be preceded by 0. Because 1 means an exact match. An IP address plus a subnet mask can specify a network segment. Then the subnet mask is 1 is the network bit. A subnet mask of 0 is the host bit. It is mutable. All the network bits we stipulated are filled with 0. This is the address of a network segment. So the mask must be consecutive. Can't be out of order. Continuous means it has to be 11110000 instead of 110101. Then the anti-mask we said before is turn this 0 into a 1 based on the mask. Then turn 1 into 0. Just like we talked about the OSPF announcement earlier. The original 24-bit mask declares a network segment. Should be 24-1. Then 8 zeros. When we declared it was 24 zeros and 8 1s. Its anti-mask is composed of consecutive 0 and 1. And 0 and 1 cannot be out of order. Must be preceded by 0. 1 after. This is called anti-masking. Then, for the anti-mask. It is actually such a relationship with the positive mask. Exactly the opposite. So what will use the anti-mask? Just like OSPF and EIGRP. All anti-masks are used. We're talking about wildcards today. Wildcards are the only thing we will touch this concept in ACL in the NA phase. Called wildcards. We call it the jump mask. Pay attention to my words. It is composed of discontinuous 1 and 0. And it is for us. 1 is random. 0 is an exact match. 1 in the mask is an exact match. 0 in the anti-mask is an exact match. Then 0 in the wildcard is an exact match. This might sound a little difficult to understand. The latter two as examples. The first one is too regular, so don't look at it. Let's calculate the two harder. First look at 192.168.1.0. Its wildcard is 0.0.0.254. 0 means it is an exact match. This 0 means that the first 8 bits are all 0. The first 8 digits represent 192. It is fixed. Let's just say. In fact, we don't need to be so clear about the realization stage. But you have to understand. Now the first 3 digits are all 0. Represents 192.168.1. This is an exact match. Then the next bit is 0. It's actually 8 zeros. 0 0 0 0 0 0 0 0. This 254 is 255 minus 1. The last of these 8 bits is 1. So 254 should be 1111110. Now corresponds to this bit of 0. Represents an exact match. The first 7 digits represent any. The last 0 is an exact match. So when we calculate, let's see what changes these 7 can bring. Let's say a few simple. Here side can be written as 00000010. 0 is the last digit. Is precise. This bit can become 1. Then I add 1 up. Becomes 00000100. Further down it becomes 00000110. The last digit is fixed to 0. This bit actually changes between 0 and 1. Actually, at the beginning, this bit can be 0. To us. If it is 0, represents 0. If here is 1, represents 2. If the previous digit is 1, represents 4. If these 2 bits are 1, it represents 6. So, if you write wildcards like this, what it actually matches is from 192.168.1.0. All even numbers up to 192.168.1.255. It matches actually all even numbers. Because for the entire 8-bit binary, 128 from the first, 64, 32, 16, 8, 4, 2, 1. Only the last digit is odd. So if the last bit is fixed to 0, then it means that, no matter how the previous numbers are combined, it is impossible to calculate an odd number. It is always even. So if we use the last digit is 254, then it represents, in this range, you will match all even numbers. As the name suggests. If I change the last bit to 1 here, then you will match all the odd numbers here. Because this one will always take the value. No matter how the above even numbers take value. Just add an odd number at the end. It's an odd number. In fact, it is not very useful at this stage. But in the future when you learn protocols like BGP, you'll see wildcards again. So now let's just understand. Let's briefly talk about this 254. For 254. The last one it is 1.0. After 1.0 this is a 254. It means that here are 7 ones and 1 0. Then the rear is a 0. Then below this is 0. Represents that the last digit is fixed. Only this is a 254. The last bit in 254 is 0. Then it is actually 0001. So when we go to match, it is equivalent to matching all even numbers in this interval. Look at the 254 just now. It's just the last one. Now this 254 is placed in the middle. This is a 1. Is 00000001. It is 11111110. Represents that except the last one is 1. Everything else is arbitrary. I also said, it will match all odd numbers in the interval in this range. Because the last bit has a value of 1. No matter how you add it to the front. The front is mutable. No matter how it changes. It is an odd number. It is equivalent to if we use this form. 192.168.1.0. Its wildcard is like this. It is equivalent to this 192.168.x.0 that it matches. X is any number. That is, all odd-numbered network segments. For example, 192.168.1.0, 3.0, 5.0, 7.0 etc. So we call the wildcard a jumping inverse mask. You may find it difficult to listen. You can watch the video several times after class. You need to know what it means. Here's what we're talking about: masks and wildcards. Actually, our ACL is finished. If for basic ACL configuration, you want to match the previous network segment, dedicated to killing a network segment, you can try to configure it yourself after class. The command is like this. Enter a matching IP address. Add a wildcard after the IP address. Usually, if it is a 24-bit network segment, followed by 30 and a 255 on the line, under the adaptation range of a relatively regular network segment. It actually looks the same as the anti-mask. Unless you have special needs in the future, you have to use wildcards again to calculate. At this stage, you can understand it as an anti-mask. Okay. Above this is the ACL. Let's talk about the next experiment. We are going to learn NAT. For NAT, we will configure while teaching. I turn it off first. Let's start the next experiment. I have to open it first. Otherwise, it will be a little slow to load in a while. This is an experiment with NAT. Like ACL and NAT. Actually, they are very simple. It's for experimentation. First, let's talk about the NAT scenario. So let's discuss a question. It is known. The address we are using now is an IPv4 address. Now the overall network environment uses IPv4. Remember how many IPv4 addresses there are in the world? When we talked about IP addresses before. A total of 32 bits. Each bit has two values 0 and 1. That is 2 to the 32nd power. About 4.29 billion addresses. Less than 4.3 billion. The world now communicates using IP addresses. As long as the device wants to connect to the internet, must have an address. That is, now all devices that can be controlled through the network, it will have an IP address. For the world, 4.3 billion addresses are not enough. We said it before. We will use private network addresses internally, and run the public network address on the public network. Then everyone will have heard a sentence. The private network address cannot run on the public network. The public network does not forward the traffic of the private network IP address. Why doesn't it forward it? For example, 192.168. This is a standard C-class private address range. An address like this, since it is a private address, it means that we can use, whether at work or at home, even a small restaurant outside, for such an address that everyone can use. If someone sends a data in the future, go to 192.168.1.1. The data reaches the carrier's device. If it can really help you retweet. So where is this address? For the whole world. Use an address segment like 192. So many private addresses. It does not know which 1.1 you are going to. So it will not help you with data forwarding. That is, because the addresses of these hosts in our internal private network has too much overlap. So when the operator forwards, it will appear confusing. So it can't help you retweet, since it can't be forwarded. How do I get online now? We are now deploying a technology on export called NAT, Network Address Translation. It is possible to convert between addresses. That is, when we are sending data, we're going to convert the data to it. We modify the original address of the data. Then we can convert the private network address into a public network address. Form a local mapping information. Then I can send data. Then if the future data is returned, when I receive data, will be based on the current destination address in this local mapping information table, to see if there is this record. If so, then we convert the address back to, that is, change this destination address to a source IP of the private network in the NAT table. This is the idea of NAT. Modify the source address of the data when sending. Change to a public network address. Form a message locally and send it out. When receiving data in the future, send it to this public address. Then I check in the local mapping table. Is there a private network address converted to this public network just now? If there is, I will change the current destination address to the original source IP address of this private network. Send this data again. It might be more abstract.